Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Here's something that should keep you up at night, but probably won't. Right now, as you're listening to this, you are bathed in the faint ancient glow of the universe's very first light. It's not visible light, but it's there, omnipresent, coming from every direction in the cosmos, carrying information from a time when the universe was less than 400,000 years old. Barely an infant compared to its current 13.8 billion years. This isn't some abstract theoretical concept. It's a measurable, tangible echo of creation, a whisper from the very beginning of everything. Imagine looking at a baby picture of the entire universe, not a photograph taken by a camera, but light itself, stretched and cooled over unimaginable cosmic distances and timescales. This light, known as the cosmic microwave background, is the oldest light we can ever hope to see, a direct remnant of a time when the universe was a superheated, dense fog, utterly unlike the vast, dark, star-filled space we know today. It's a universal hum, a constant static that permeates all of reality, telling us a profound story. The universe had a beginning, it was incredibly hot and dense, and it has been expanding and cooling ever since. It's a scientific Rosetta Stone, allowing us to decode the earliest moments of existence. This isn't just a quirky scientific fact, it's the foundational cornerstone of our understanding of the cosmos, a definitive proof of the Big Bang. And the more we learn about this ancient light, the more mind-boggling the universe's story becomes. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing this exploration of scientific wonder is reaching people all over the world at all hours of the day and night. Let's begin with a question that seems almost philosophical, but has a deeply scientific answer. What does empty space actually look like? Most of us would picture a perfect vacuum, utterly devoid of anything, cold, dark, silent. But that mental image, while intuitively appealing, is profoundly incorrect. Even the most desolate stretches of intergalactic space are not truly empty. They are in fact filled with a faint uniform glow of microwave radiation, a kind of cosmic static that permeates every corner of the observable universe. This isn't noise, it's a message, the oldest message we've ever received, telling us about the universe when it was just a tiny fraction of its current age. To truly appreciate this, let's first ground ourselves in what we mean by microwaves. You're probably familiar with microwaves in your kitchen, heating up leftovers. Those microwaves are a form of electromagnetic radiation, just like visible light, radio waves, X-rays, and gamma rays. They all travel at the speed of light, but they differ in their wavelength and frequency, which determines their energy. Microwaves sit between radio waves and infrared light on this spectrum, with wavelengths typically ranging from a millimeter to a meter. Your microwave oven uses waves around 12 centimeters long to excite water molecules in food, generating heat. Your Wi-Fi router also uses microwaves, albeit at lower power, to send data wirelessly. So, when we talk about cosmic microwaves, we're talking about the same fundamental phenomenon, just on a vastly different scale and originating from a far more profound source. Now, imagine billions of years ago, long before any stars or galaxies existed. The universe wasn't the cold, dark, vast expanse we know today. Instead, it was an incredibly hot, incredibly dense soup of fundamental particles, mostly protons, electrons, and photons. Think of it less like a vacuum and more like the inside of a star, but everywhere, all at once, and expanding rapidly. In this primordial plasma, electrons weren't bound to protons to form neutral atoms. They were free, whizzing around, constantly scattering photons. This meant that photons, particles of light, couldn't travel very far without bumping into an electron and getting knocked off course. The universe, in effect, was opaque, like a thick glowing fog. You couldn't see anything because light couldn't travel freely. This situation persisted for approximately 380,000 years after the Big Bang. During this time, the universe was expanding, and as it expanded, it cooled. Temperature and density are intimately linked in a gas or plasma. As the universe got bigger, the particles spread out, and their average energy decreased. Eventually, the temperature dropped to a critical point, about 3,000 Kelvin. To put that in perspective, the surface of our Sun is around 5,778 Kelvin, so 3,000 Kelvin is still incredibly hot, hot enough to make hydrogen glow bright red. But this specific temperature was crucial because it was cool enough for free electrons to finally combine with protons to form stable, neutral hydrogen atoms. This event is called quote 3, even though the particles had never been combined before, so some prefer the term quote 4 to describe the moment photons separated from matter. When these electrons and protons combined, the vast sea of free electrons largely disappeared. Suddenly there were far fewer charged particles to scatter photons. It was as if a dense fog had instantly lifted, revealing a clear sky. The photons, which had been trapped and bouncing around for hundreds of thousands of years, were now free to travel unimpeded. They streamed out in every direction, carrying with them a snapshot of the universe at that exact moment, the moment it became transparent. This was the fifth of the universe, and it was incredibly energetic, mostly in the form of visible and infrared light, glowing brightly at that 3,000 Kelvin temperature. But here's where the cosmic expansion comes into play. Those photons, released 13.8 billion years ago, have been travelling through an expanding universe ever since. As the universe expands, it stretches the very fabric of space-time, and as space-time stretches, it stretches anything travelling through it, including the wavelengths of light. This phenomenon is called redshift. Imagine a wave drawn on a rubber sheet. If you stretch the sheet, the wave gets longer. The same thing happens to light waves in the expanding universe. The energetic, short wavelength photons from the early universe have been stretched and stretched over billions of years, their wavelengths growing longer and longer, shifting them from visible light through infrared and finally into the microwave portion of the electromagnetic spectrum. When Arno Penzias and Robert Wilson, two radio astronomers at Bell Labs, accidentally discovered this omnipresent hum in 1964, they initially thought it was equipment malfunction. They tried everything, cleaning pigeon droppings off their antenna, recalibrating their instruments, even testing for urban interference. But the signal persisted, a faint uniform noise coming from every direction in the sky, day and night, regardless of where their antenna was pointed. It was a perfect, isotropic background noise, equivalent to a temperature of about 3.5 Kelvin. What they had found was precisely what theorists like George Gamow, Ralph Alpha, and Robert Herman had predicted in the 1940s. The relic radiation from the Big Bang, redshifted into microwaves. Modern measurements, most notably by the COBE, WMAP, and Planck satellites, have refined this temperature to a precise 2.725 Kelvin, or about negative 270 degrees Celsius, just a few degrees above absolute zero. This cosmic microwave background, or CMB, is arguably the strongest piece of evidence we have for the Big Bang theory. It's not just a theory anymore, it's an observed reality. We can literally see the aftermath of the universe's fiery birth. The uniformity of the CMB across the sky tells us that the early universe was incredibly smooth and homogeneous. However, the exquisite sensitivity of modern instruments has also revealed tiny, subtle fluctuations in this temperature, variations of only a few parts in 100,000. These minuscule temperature differences, which correspond to slight density variations in the early universe, are incredibly important. They are the seeds, the gravitational imperfections, from which all the large-scale structures we see today, galaxies, galaxy clusters, and vast cosmic filaments, eventually grew. So, when you look up at the night sky, or even when you simply exist, remember that you are constantly being bathed in this ancient light. It's an omnipresent reminder of our cosmic origins, a direct link to the universe's infancy. It's the universe's baby picture, and it tells us that everything started from a hot, dense state and has been evolving ever since. This incredible echo of creation, the CMB, gives us a profound glimpse into the universe's past, revealing its initial conditions. But what exactly was that initial hot, dense state? How did it come to be? And what were the very first moments of the universe truly like, before even this first light could escape? That takes us even further back, to a realm where our current physics begins to stretch and grapple with concepts that push the very limits of our imagination, and that's precisely what we'll explore in our next journey into the universe's earliest moments. We've journeyed back to the universe's baby picture, that incredible cosmic microwave background radiation, the ancient light that started its journey when the cosmos was just 380,000 years young. It's a tangible echo, a whisper from the past telling us so much about the universe's infancy. But what if we could rewind the cosmic tape even further? What if we could peer into the moments before that first light could escape, into the very Genesis spark? That's where our journey takes a truly mind-bending turn, because what we're talking about now is not just a hot, dense plasma. It's a realm where our everyday understanding of reality begins to warp, where the fundamental forces we know and love were once indistinguishable. It's a place beyond our direct observation, yes, but one we can reconstruct with astonishing precision, using the laws of physics as our guide. Imagine, if you will, a universe not just filled with a thick glowing fog, but one that was that fog compressed into an unimaginably small, incredibly hot and dense point. This isn't just a metaphor, it's the core idea behind the Big Bang theory. And let's be clear, right from the start, about a common misconception. The Big Bang wasn't an explosion in space. It was an explosion of space itself. You weren't standing outside of it, watching it expand into some pre-existing void. Oh no, you were the void, stretching, growing, unfolding in every direction simultaneously. Think of it like baking a loaf of raisin bread. As the dough rises, the raisins move farther apart from each other, but they aren't moving through the dough. The dough itself is expanding, carrying the raisins along for the ride. Or consider a balloon being inflated, with dots drawn on its surface. As the balloon expands, the dots move apart. Not because they're crawling across the rubber, but because the rubber itself is stretching. That rubber, in our cosmic analogy, is space-time. And in the earliest moments, that rubber was stretching at an utterly mind-boggling, incomprehensible rate. So we're not just talking about a universe that was a little bit hotter and denser than the CMB. We're talking about conditions so extreme that the very fabric of existence, the forces that govern everything we see, hear, and touch, were radically different. Let's dial the clock back, not to 380,000 years, but to the first second of the universe's life. Can you even fathom that? A single second. In that fleeting blink, an entire cosmos, the progenitor of everything we know, was taking shape. At the very earliest moments, we can even begin to conceptualize. A tiny fraction of a second after the Big Bang, perhaps 10 to the negative 36 seconds, the universe was so incredibly hot and energetic that the four fundamental forces we experience today, gravity, electromagnetism, the strong nuclear force and the weak nuclear force, were likely unified into a single superforce. It's a concept that sounds like science fiction, doesn't it? But it's a cornerstone of our theoretical understanding of the very, very early universe. As the universe expanded and cooled ever so slightly, gravity was the first force to break away from this unified superforce. Imagine a perfectly symmetrical snowflake, and then, as it warms just a little, one tiny branch begins to differentiate itself. That's a simplified way to think about it. This period, where gravity became distinct, is often called the Grand Unification Epoch. We're talking about temperatures so high, energies so immense, that our current particle accelerators can't even come close to replicating them. This is pure theoretical physics, where we push the boundaries of what's possible to imagine. Then, around 10 to the minus 12 seconds, the strong nuclear force which binds quarks together to form protons and neutrons separated, and finally, the electromagnetic force and the weak nuclear force which governs radioactive decay split apart. This left us with the four distinct forces we observe today. It's like watching a single, primordial entity differentiate into the complex interacting system we now inhabit. But what was the universe made of during these unfathomably brief moments? Not atoms, not even protons and neutrons. We're talking about a superheated primordial soup of fundamental particles, quarks, leptons, like electrons, and their antimatter counterparts, along with a sea of photons and neutrinos. This was the quark-gluon plasma, a state of matter so exotic that scientists at places like CERN, with their massive particle colliders, work tirelessly to briefly recreate it, trying to catch a glimpse of the universe's earliest form. In this plasma, quarks and gluons zipped around freely, unbound by the strong force that would later shackle them into composite particles. It was a chaotic, energetic dance. Then, as the universe continued its rapid expansion and cooling, just a few microseconds after the Big Bang, something profound happened. Quarks began to bind together. 3 quarks formed protons, 3 quarks formed neutrons. This was the birth of the building blocks of atomic nuclei. Now, a quirky scientific fact for you. For every particle of matter formed, an antiparticle was also created. So in this early universe, there should have been equal amounts of matter and antimatter. And when matter and antimatter meet, they annihilate each other in a burst of energy. If this had happened perfectly evenly, the universe would be nothing but photons today. No stars, no galaxies, no us. But thankfully there was a tiny, minuscule asymmetry, about 1 part in 1 billion more matter than antimatter. This tiny imbalance is the reason we exist. It's the cosmic lottery ticket that allowed a universe made of stuff to emerge from the annihilation. So, by about 1 second after the Big Bang, the universe was filled with a hot, dense mixture of free protons, neutrons, electrons, neutrinos, and photons, still too hot for stable atomic nuclei to form, let alone neutral atoms. It was a universe on the cusp of creating the elements, but still in its most fundamental chaotic phase. But even this incredible story of the first second doesn't explain everything. When scientists first developed the Big Bang theory, they ran into some perplexing problems. For instance, why is the CMB so incredibly uniform across the entire sky? If different regions of the early universe were too far apart to ever interact, how did they reach the same temperature? This is known as the quote 10. Another puzzle was the quote 11. Why is the universe's geometry so perfectly flat, right on the knife edge between expanding forever and eventually collapsing? And then there was the monopole problem, predicting the existence of exotic, heavy particles that we just don't see. Enter cosmic inflation. This isn't just a tweak to the Big Bang. It's a spectacular expansion of the theory, proposed in the early 1980s by physicists like Alan Guth. Inflation suggests that in the very, very first fraction of a second, from about 10 to the minus 36 seconds to 10 to the minus 32 seconds after the Big Bang, the universe underwent an absolutely mind-boggling exponential growth spurt. We're talking about space expanding faster than the speed of light, not through space, but space itself stretching, making the universe grow by a factor of at least 10 to the 26th power. That's a 1 followed by 26 zeros, in an unimaginably short span of time. Imagine a tiny quantum fluctuation, smaller than an atom, suddenly inflating to the size of a grapefruit, and then almost instantly to the size of a galaxy, and then far, far beyond. That's the power of inflation. This rapid, dramatic expansion essentially smoothed out any initial irregularities, solving the horizon problem by bringing causally disconnected regions into contact before inflation stretched them apart. It also flattened the geometry of the universe, solving the flatness problem, and it diluted any problematic exotic particles, solving the monopole problem. Perhaps most importantly for our story, inflation took microscopic quantum fluctuations, tiny random jitters in the energy density of the early universe, and stretched them across cosmic scales. These stretched out fluctuations became the seeds, the initial density variations that would eventually grow over billions of years into the vast structures we see today: galaxies, clusters of galaxies, and the cosmic web itself. And where do we see the evidence for these seeds? You guessed it, in the tiny temperature anisotropies, the subtle hot and cold spots in the cosmic microwave background. The CMB isn't perfectly uniform. It has these ripples, these infinitesimal variations. They are the direct imprint of those quantum fluctuations amplified by inflation. It's like looking at the ripples in a pond and knowing the exact stone that was dropped in, even if the pond has since expanded to an ocean. So, inflation provides a powerful and elegant explanation for the universe's large-scale structure and the remarkable uniformity of the CMB. It bridges the gap between the quantum realm of the very early universe and the macroscopic cosmos we observe. But even with inflation, there's a frontier, a boundary beyond which our current physics simply cannot go. This is the Planck epoch, the first 10 to the minus 43 seconds after the Big Bang. At this incredibly early time, the universe was so dense, so hot, and so tiny that the effects of quantum mechanics and general relativity, our theory of gravity, become equally important. Our current theories cannot reconcile these two pillars of modern physics into a single, cohesive framework at these extreme conditions. This is where we need a theory of quantum gravity, string theory, loop quantum gravity, or something entirely new to truly understand what happened. What we can say is that in this Planck epoch, the universe was a place of pure energy, a singularity where space and time as we understand them likely didn't even exist in their current forms. It's the ultimate mystery, the absolute beginning, the moment before even the most fundamental particles and forces began to differentiate. So, when we look at the cosmic microwave background, that ancient light we discussed in Chapter 1, we're not just seeing the moment atoms formed, we're seeing a reflection of inflation, a fingerprint of these quantum fluctuations, and an echo of a universe that began in an unimaginable flash of energy and expanded with an almost violent grace. It's a universe that, in its very first moments, laid down the blueprint for everything that would follow. We've travelled from the universe's first visible light back to the edge of the known, to the very spark of creation. We've seen how a hot, dense soup of fundamental particles evolved, how forces separated, how inflation smoothed and seeded the cosmos. And yet the ultimate question remains: what truly caused that spark? What lies beyond the Planck epoch? It's a question that continues to drive physicists and cosmologists to push the boundaries of knowledge, to dream of new theories, and to look for even fainter echoes of the universe's earliest, most profound secrets. The journey of discovery, my friends, is far from over. We left off, didn't we, peering into that most enigmatic of cosmic curtains, the Planck epoch. That infinitesimally small sliver of time, the first 10 to the minus 43 seconds after the Big Bang, where the universe was so unfathomably hot, dense, and tiny that our most cherished theories, quantum mechanics and general relativity, simply refused to play nice together. It's like trying to fit a square peg into a round hole, or perhaps more accurately, trying to describe the intricate dance of subatomic particles using the broad strokes of cosmic gravity. It just doesn't work. This, my friends, is where our current understanding hits a fundamental wall, a cosmic do not enter sign for physicists. But humanity, you know us. We're not ones to be deterred by a mere wall. We want to know what's behind it. This insatiable curiosity drives us to seek a unified theory, a grand framework that can describe all of nature's forces, including gravity, at every scale. This is the holy grail of modern physics, quantum gravity. Imagine, if you will, a theory so elegant, so profound, that it could explain the birth of the universe, the inner workings of black holes, and the very fabric of space-time itself. Wouldn't that be something? One of the most ambitious attempts to bridge this chasm is string theory. Now, don't let the name intimidate you. The basic idea is wonderfully simple, yet mind-bendingly profound. What if the fundamental particles we think of as point-like, electrons, quarks, photons, aren't actually points at all? What if instead they are tiny, one-dimensional vibrating strings? Think of it like a violin string. Depending on how it vibrates, it produces different musical notes. In string theory, different vibrational modes of these fundamental strings correspond to different particles, each with its unique mass and charge. It's a cosmic symphony, where particles are just different notes played on these incredibly tiny strings, and here's where it gets even wilder. For string theory to work mathematically, it requires extra spatial dimensions beyond the 3 we experience every day, plus time. We're talking about 10 or even 11 dimensions. Where are they, you ask? Well, the theory suggests these extra dimensions are compactified, curled up so incredibly tightly, perhaps at the Planck scale, that we can't perceive them. They're like a garden hose. From far away, it looks like a one-dimensional line, but up close, you see its two-dimensional surface. These hidden dimensions could hold the key to unifying all the forces, including gravity, into a single, cohesive picture. It's a beautiful, if currently untestable, vision of reality. Another contender, loop quantum gravity, takes a different approach. Instead of tiny strings, it tries to quantize space-time itself. It suggests that space-time isn't a smooth, continuous fabric, but rather a granular, discrete structure, woven from incredibly tiny loops or networks. Imagine zooming in on a digital image until you see the individual pixels. Loop quantum gravity proposes that space-time is similarly pixelated, with these fundamental loops forming the pixels of gravity. It's an attempt to build gravity from the ground up, quantum style, without needing extra dimensions. Both string theory and loop quantum gravity offer tantalizing glimpses into what might have occurred during the Planck epoch, promising to describe the universe when it was a quantum foam of space-time. They are our best theoretical bets for unlocking the ultimate secrets of creation, but remember, they are still theories, mathematical frameworks we are exploring. We don't yet have the experimental evidence to definitively confirm either, or perhaps even a completely different idea altogether. The universe, in its infinite wisdom, holds its cards close to its chest when it comes to its absolute genesis. So, while we continue our quest for quantum gravity, let's fast forward a bit past the Planck epoch, past inflation, past the formation of the cosmic microwave background. Let's leap billions of years into the present, to the universe we observe today. Because even with all our incredible insights into the early cosmos, our current universe presents us with two of the most profound and baffling mysteries of all: dark matter and dark energy. You see, for decades, astronomers have been meticulously mapping the cosmos, observing the galaxies, clusters and superclusters that populate the vast expanse, and what they've found is frankly perplexing. Take a galaxy, any galaxy. We can measure how fast the stars and gas clouds orbit its centre. Based on the visible matter, the stars, the gas, the dust, we can calculate how much gravitational pull there should be, and thus how fast things should be orbiting. But here's the kicker: they're orbiting much, much faster than they should be. It's like a merry-go-round spinning so fast that the children on it should be flung off, yet they remain firmly in place. There must be something else, some invisible mass holding them together. This something else is what we call dark matter. It's dark because it doesn't emit, absorb or reflect any light or electromagnetic radiation, making it completely invisible to our telescopes. And it's matter because it exerts a gravitational pull. The evidence for its existence is overwhelming and comes from multiple independent observations. We see it in the rotation curves of galaxies, where the outer regions spin just as fast as the inner ones, implying a massive invisible halo surrounding them. We see it in gravitational lensing, where the light from distant galaxies is bent and distorted by the immense gravity of foreground galaxy clusters, much more than the visible matter alone could account for. Perhaps the most compelling evidence comes from the bullet cluster. This is a spectacular cosmic collision where two galaxy clusters have passed through each other. When we observe it, we see the hot gas, which makes up most of the visible mass of the clusters, has been slowed down and separated from the main gravitational centers. But the gravitational centers, mapped by gravitational lensing, have continued right through, unimpeded. This is exactly what we'd expect if the bulk of the mass in these clusters is made of something non-interacting, something dark that simply sailed past itself while the ordinary matter, the gas, got tangled up. So, what is dark matter? We know it's not ordinary matter like protons and neutrons, baryonic matter, because we have precise measurements of the amount of baryonic matter in the universe from the Big Bang nucleosynthesis and the CMB. It doesn't interact with light, so it's not stars, planets, or black holes. The leading candidates are exotic, yet to be discovered particles like WIMPs, weakly interacting massive particles, or axions. Scientists are actively searching for these elusive particles in underground laboratories, hoping to detect the incredibly rare occasions when a WIMP might bump into an atomic nucleus, or when an axion might convert into a photon. It's a painstaking, challenging search, but the payoff, discovering a completely new form of matter that makes up nearly 27% of the universe, would be truly revolutionary. But wait, there's another piece to this cosmic puzzle, an even more bewildering constituent that dominates the universe's energy budget: dark energy. For most of the 20th century, cosmologists expected the expansion of the universe, set in motion by the Big Bang, to be gradually slowing down due to the gravitational pull of all the matter within it. It was like throwing a ball into the air. You expect it to slow down as gravity tugs on it. The big question was not if it was slowing down, but how fast. Then came the late 1990s and a series of groundbreaking observations using Type Ia supernovae. These particular supernovae are what we call standard candles, because they always explode with roughly the same intrinsic brightness. By measuring their apparent brightness from Earth, astronomers can determine their distance. And by also measuring their redshift, they can determine how fast the universe was expanding at different points in its history. The results were utterly shocking. The universe isn't slowing down, it's speeding up. Its expansion is accelerating. Imagine throwing that ball into the air expecting it to slow down, but instead it starts rocketing upwards even faster. This discovery earned the Nobel Prize in Physics in 2011, and it plunged cosmology into a new era of mystery. What force could possibly be pushing the universe apart, overcoming the collective gravity of all matter and dark matter? We call this mysterious, pervasive force dark energy. Dark energy is not a particle like dark matter. It's more like a property of space itself, a kind of intrinsic energy density that causes space to expand. One leading candidate is Einstein's famous cosmological constant, a term he initially introduced into his equations of general relativity to create a static universe, then famously called his biggest blunder when Hubble discovered the universe was expanding. It turns out Einstein might have been right all along, just for the wrong reasons. If the vacuum of space itself has energy, then as space expands, more vacuum is created, and thus more dark energy, leading to an ever-increasing outward push. Another idea is quintessence, a dynamic, evolving energy field that permeates space. Unlike the cosmological constant, quintessence could change over time, and its properties might determine the ultimate fate of the universe. But for now, dark energy remains the most enigmatic component of our cosmos, making up a staggering 68% of the universe's total energy and matter content. So, let's take stock, shall we? Our universe, the grand stage for all existence, is composed of roughly 5% ordinary matter, the stuff we see, touch, and are made of: stars, planets, gas, dust. 27% dark matter, the invisible gravitational glue holding galaxies and clusters together. 68% dark energy, the mysterious force accelerating the expansion of the universe. Isn't that absolutely wild? Everything we perceive, everything we've ever studied with our senses and our telescopes, makes up less than 5% of reality. The vast majority of the universe is made of things we cannot see, cannot touch, and barely understand. It's a humbling thought, isn't it? It tells us how much more there is to learn, how many more layers of cosmic reality are waiting to be peeled back. These two dark components aren't just fascinating curiosities. They are fundamental to understanding the universe's past, present, and most crucially, its future. The delicate balance, or rather, the overwhelming dominance of dark energy, has profound implications for how our cosmic story will ultimately unfold. And that, my friends, is a tale for our next chapter, as we turn our gaze from the beginning towards the inevitable, yet uncertain, end. Alright, let's talk about the future. Because if the universe is telling us a story, it's not just about how it began, it's also about where it's going. We've journeyed through the cosmic infancy, the tumultuous first seconds, and confronted the profound mysteries of dark matter and dark energy, those invisible architects that shape our cosmos. Now, we turn our gaze to the ultimate fate, the grand finale orchestrated by these very forces. You see, for most of cosmic history, the prevailing thought was that the universe's expansion would eventually slow down, perhaps even reverse. It was a cosmic tug-of-war, the outward push of the Big Bang versus the inward pull of gravity from all the matter within it. For a long time, the question was simply, would gravity win? Would the universe one day collapse back in on itself in a spectacular, quote, 19 perhaps, to be reborn in a new Big Bang? Or would it expand forever, eventually fading into a cold, dark oblivion? Then came the late 1990s, and the universe, in its infinite wisdom, threw us a curveball, a huge one. Observations of distant Type Ia supernovae, those brilliant standardized cosmic lighthouses we talked about, revealed something astonishing. Not only was the universe expanding, but its expansion was accelerating. It was speeding up. This wasn't just a slight deviation. It was a fundamental shift in our understanding of the cosmos, hinting at a dominant, pervasive force that pushes space apart. That force, as we've established, is dark energy. Imagine a giant invisible hand, gently but relentlessly pushing everything farther and farther apart. That's dark energy. It's not just overcoming gravity, it's winning. And because of this relentless acceleration, the universe's most likely future is not a fiery crunch, but a slow, cold fade into oblivion. We call this the quote 20 or the quote 21 of the universe. It sounds bleak, doesn't it? But let's unpack what that truly means. The concept of heat death is deeply tied to one of the most fundamental laws of physics, the second law of thermodynamics. This law tells us that in any isolated system, entropy, a measure of disorder or randomness, always increases over time. Think about it in your own home. A clean room tends to get messy, a hot cup of coffee cools down, an ice cube melts. These are all processes where energy disperses and disorder increases. The universe as a whole is essentially the ultimate isolated system. So, in the big freeze scenario, what we're looking at is the universe gradually running out of usable energy. It's not about temperature necessarily dropping to absolute zero everywhere at once, but rather about everything reaching a state of uniform maximum entropy. No more hot spots, no more cold spots, no more energy gradients to drive processes like star formation or life. Let's fast forward through the unimaginable timescales involved. Billions of years from now, our sun will become a red giant, then a white dwarf. Other stars too will exhaust their nuclear fuel. The smallest stars, red dwarfs, might burn for trillions of years, but even they will eventually fizzle out. Galaxies, once vibrant nurseries of stars, will become increasingly dimmer, populated by the cold remnants of stellar evolution, white dwarfs, neutron stars, and black holes. And here's where dark energy really starts to flex its cosmic muscles. As the universe accelerates its expansion, galaxies will move farther and farther apart. Right now, our local group of galaxies, which includes Andromeda and the Milky Way, is gravitationally bound, and we're actually on a collision course with Andromeda. But beyond our immediate neighborhood, other galaxy clusters are already receding from us. Eventually, due to dark energy, even gravitationally bound clusters will find themselves isolated. The light from distant galaxies will become so stretched, so redshifted by the expansion of space, that it will eventually fade beyond detectability. Imagine looking up at the night sky billions of years from now and seeing nothing. Just an empty, dark expanse. No other galaxies visible, only the fading embers of our own. We will be truly alone in the vast cosmic ocean. The universe will continue its inexorable march towards darkness. Stars will die. Planets will wander aimlessly through the frigid void. Then the black holes, those cosmic behemoths, will take center stage. They are incredibly long-lived, but even they are not immortal. According to Stephen Hawking's brilliant theoretical work, black holes slowly evaporate through a process called Hawking radiation. Over timescales that make the age of the universe look like a blink of an eye. Think 10 to the 67th years for a stellar mass black hole, and 10 to the 100 years for supermassive ones. These ultimate gravitational prisons will radiate away their mass, eventually disappearing into a puff of photons and other elementary particles. What's left after all of this? A universe filled with an extremely dilute soup of photons, neutrinos, electrons, and positrons, spread so thinly across an unimaginably vast and ever-expanding space that interactions will be virtually non-existent. Everything will be at the same, incredibly low temperature, just barely above absolute zero. No energy differences, no structure, no change. Just a uniform, cold, dark, and empty void. That, my friends, is the heat death. A universe where nothing ever happens again. Now, while the big freeze is our current best bet based on our understanding of dark energy, it's not the only theoretical possibility. What if dark energy isn't constant? What if its density somehow increases over time? If that were the case, its repulsive force could grow so strong that it wouldn't just pull galaxies apart. It would eventually overcome all fundamental forces. This terrifying scenario is known as the Big Rip. In a Big Rip, the accelerating expansion would intensify to such an extreme degree that it would first tear apart galaxy clusters, then individual galaxies, then solar systems, then planets. Eventually, the force would be so powerful that it would overcome the electromagnetic and strong nuclear forces, ripping apart atoms themselves. Protons and neutrons would be torn asunder, followed by the very fabric of space-time, until everything, every particle, every quantum field, is scattered into an infinitely dilute, disconnected void. It's a violent, cataclysmic end, a complete shredding of reality. Thankfully, current data suggests that dark energy's density is constant, or very nearly so, making the Big Rip a less likely, though still fascinating theoretical possibility. And the Big Crunch? That once popular idea where gravity wins and the universe collapses back in on itself? With the discovery of accelerating expansion, the Big Crunch has largely been relegated to the realm of theoretical what-if scenarios. Unless dark energy somehow reverses its repulsive nature and becomes attractive, which we have no evidence for, a cosmic recollapse is not in our universe's future. Let's return to the implications of this accelerating expansion on our own perspective. We often talk about the observable universe, the sphere of space from which light has had time to reach us since the Big Bang. But as space expands and accelerates, the light from increasingly distant objects will take longer and longer to reach us, eventually never reaching us at all. It's like standing on a treadmill that's speeding up. The finish line just keeps getting farther away. What this means is that our cosmic horizon is effectively shrinking. Galaxies that are currently observable will, in the unimaginably distant future, recede beyond our view. If there are advanced civilizations billions of years from now, they will look out into the cosmos and see only their own galaxy, perhaps a few close neighbours, against a backdrop of utter blackness. They would have no way of knowing about the billions of other galaxies that once populated the universe, no way of discovering the cosmic microwave background, no way of understanding the Big Bang itself. All the evidence of our universe's grand history, its incredible diversity, its dynamic evolution, would be forever hidden from them. We are, in a very real sense, living in a privileged time, a cosmic sweet spot where the universe's past and its vastness are still visible to us. It's a sobering thought, isn't it? From the Planck epoch, that infinitesimal sliver of time at the very beginning, to the ultimate heat death, The universe has a story arc that is both magnificent and, in its conclusion, profoundly melancholy. We, as curious beings, are piecing together this narrative, understanding the forces that shaped it and those that will ultimately unmake it. But don't let the thought of a cold, empty future diminish the wonder of the present. The journey of discovery is the true marvel. To understand that we are made of stardust, that we carry within us the echoes of the Big Bang, and that our minds can grasp the immensity of cosmic time and space, that is the real triumph. We are unravelling the universe's secrets, from its fiery birth to its inevitable, quiet end, and that, in itself, is a story worth telling, worth exploring, and worth cherishing every moment of our brief, brilliant existence within it. So, as we contemplate these vast timescales and unimaginable fates, we're reminded that our universe is a dynamic, evolving entity, constantly revealing new layers of complexity. And while the ultimate end may seem distant and stark, the process of understanding it brings us closer to the heart of what it means to be here, now, witnessing this incredible cosmic drama unfold. We've talked about the beginning, we've explored the present, and now we've peered into the distant future. But what if there's more to the story than just one universe? What if our cosmos isn't alone? What if the Big Bang wasn't a unique event, but one of many? That, my friends, is a question for another time, another exploration into the truly mind-bending possibilities of existence itself. We've journeyed through the universe's fiery birth, its fleeting first moments, its grand expansion, and its inevitable, chilling end. We've grappled with the invisible giants of dark matter and dark energy, the very fabric of our reality. But as we stand at the precipice of its ultimate fate, a profound question lingers, one that challenges our very perception of existence. Is our universe unique, or are we just one tiny precious bubble in an unimaginably vast cosmic ocean? This, my friends, is where the concept of the multiverse steps onto the stage. A mind-bending idea that suggests our universe, with all its stars, galaxies, and the intricate laws that govern them, might be just one among an infinite, or at least astronomically large, number of others. It's a concept that sounds like science fiction, doesn't it? But it emerges from some of our most compelling scientific theories, offering potential solutions to some of the biggest puzzles we face. Let's dive into this glorious speculative frontier, shall we? Imagine, if you will, that the cosmos isn't just one grand story, but an infinite library, each book a universe, each chapter a different set of physical laws, a different history, a different outcome. The simplest way to conceive of a multiverse, what some call a leveler multiverse, doesn't even require us to look beyond our own Big Bang. Think about it. If space is truly infinite, and the distribution of matter and energy within it is roughly uniform on the larger scales, then eventually everything must repeat. It's like an infinite deck of cards. You've got 52 cards, right? Shuffle them enough times, and eventually you'll get the same sequence again. Now scale that up to the entire universe. If there are only a finite number of ways to arrange particles within a finite volume, and you have an infinite volume, then somewhere out there, inconceivably far away, there's another you reading this exact thought. Another Earth, another solar system, another Milky Way, all arranged exactly as ours is. It's a mind-boggling thought, isn't it? You could be living out every possible permutation of your life, an infinite number of times in an infinite number of identical universes, all within the same overarching space-time. This isn't about parallel dimensions, it's about sheer statistical inevitability in an infinite expanse. But let's go deeper, because the multiverse gets truly wild when we consider a level 2 multiverse, one that springs directly from our discussion of cosmic inflation. Remember that incredible exponential expansion that smoothed out our universe and stretched quantum fluctuations into the seeds of galaxies? Well, what if inflation didn't just happen once and then stop everywhere? What if it's eternal? Imagine a cosmic foam, constantly bubbling and expanding. Within this foam, occasionally, pockets of inflation do stop, creating bubble universes like our own, where the expansion slows down, matter forms and stars ignite. But in the vast regions between these bubbles, inflation continues unabated, forever generating new bubbles. This is the concept of eternal inflation, and it's a powerful idea. If inflation is eternal, then new universes are constantly popping into existence, each one a separate, disconnected bubble in a larger, ever-inflating space-time. Now here's where it gets truly fascinating. Within each of these bubble universes, the fundamental physical constants, things like the strength of gravity, the mass of an electron, the speed of light, could be different. The very laws of physics we hold so dear in our own universe might just be our universe's specific settings. Think of it like a cosmic lottery. If you have an infinite number of universes, each with slightly different physical parameters, then it becomes far less surprising that at least one of them would have the exact right conditions to allow for the formation of complex chemistry, stars, galaxies, and eventually life. This brings us to one of the most compelling arguments for a multiverse, the fine-tuning problem. When we look at our universe, we notice something remarkable. The fundamental constants seem incredibly precise, almost tailored to allow for life. If gravity were slightly stronger, stars would burn out too quickly. If the electromagnetic force were a tiny bit weaker, chemistry as we know it might not exist. If the initial density fluctuations in the early universe were slightly off, we'd either have a universe of nothing but black holes, or one so diffuse that matter never coalesced. It's like finding a perfectly balanced pencil standing upright on its tip. It could happen by chance, but it feels incredibly improbable. The multiverse offers an elegant, if still unproven, solution. If there are countless universes, each with different settings, then it's not a miracle that we find ourselves in one with the quote, 28 settings. It's simply an observational selection effect. We can only exist in a universe that allows for our existence. This is a form of the anthropic principle, the idea that the universe must be compatible with the existence of intelligent life, because otherwise there would be no one to observe it. In a multiverse, the anthropic principle shifts from a philosophical statement to a statistical inevitability. Beyond these first two levels, the multiverse concepts become even more abstract, stretching the very limits of our understanding of reality. Consider the, say, level 3 multiverse. Often associated with the bare many worlds interpretation of quantum mechanics, you see in the strange world of quantum physics, particles don't have definite states until they're observed. They exist in a superposition of all possible states simultaneously. When an observation is made, the wave function collapses, and one specific outcome is realized. But what if, instead of collapsing, the universe splits? Every time a quantum event has multiple possible outcomes, the universe branches into separate, non-communicating realities, with each outcome realized in its own distinct universe. Imagine you're about to flip a coin. In one universe, it lands heads. In another, it lands tails. In yet another, it spins forever. Okay, maybe not that last one. Every decision you make, every quantum interaction, every random event could be causing the universe to constantly fission into an astronomical number of parallel realities. This means there's a universe where you took that job, a universe where you didn't, a universe where you said that thing differently. It's not just possible, it's happening constantly, an ever-branching tree of realities. This interpretation is highly debated, but it's a mathematically consistent way to understand quantum mechanics without the messy collapse of the wave function. Then there's the mind-bending level 4 multiverse, proposed by physicist Max Tegmark, which posits that all mathematically consistent structures exist as universes. If a mathematical structure is self-consistent and can be defined, then it exists as a physical reality. This takes the concept of the multiverse to its most extreme, suggesting that our universe, with its specific laws and constants, is just one particular mathematical structure among an infinite array of others. It implies that reality isn't just described by mathematics, it is mathematics. Our physical laws aren't just approximations of an underlying reality, they are that reality. It's a universe for every possible equation, every possible set of rules. And let's not forget the tantalizing possibilities offered by string theory and worm theory, which hint at a brain multiverse. In these theories, our entire universe might be a brain, a higher dimensional membrane, floating in a higher dimensional space, perhaps one with 10 or 11 dimensions. Other brains, other universes could exist in this same hyperspace, like sheets of paper stacked on top of each other, or even drifting past each other. What happens if these brains collide? Some theories suggest that such a collision could be the very event that triggered our Big Bang, a big bounce rather than a singular beginning. Imagine the implications. Our universe wasn't born from nothing, but from the interaction of two other universes. Now, I know what you're thinking. This all sounds incredibly cool, but where's the proof? And you're right to ask that. The biggest challenge with multiverse theories is their testability. By definition, if these other universes are truly separate, beyond our event horizon, in different dimensions, or simply causally disconnected, how can we ever observe them? How can we gather empirical evidence? For the level 1 multiverse, it's a matter of looking far enough. But far enough is likely beyond our observable universe. For the level 2 eternal inflation multiverse, some theorists propose looking for bubble collision imprints in the cosmic microwave background, anomalies that might betray the gentle nudge of another universe. But so far, nothing definitive has been found. The level 3 quantum multiverse doesn't offer direct observational evidence, as the parallel universes are meant to be non-communicating. And the level 4 mathematical multiverse is, by its nature, more of a philosophical framework than a testable hypothesis in the traditional sense. Despite the current lack of direct evidence, the allure of the multiverse is undeniable. It offers elegant solutions to deep cosmological puzzles, like the fine-tuning problem. It pushes the boundaries of what we understand about reality, space, time, and existence itself. It reminds us that our universe, as vast and incredible as it is, might be just one chapter in an infinitely larger, grander cosmic saga. So, what does this mean for us, for our journey through the beginning and end of our universe? It means that the story is far from over. It means that the canvas of reality might be infinitely larger than we ever dared to imagine. It means that the quest for knowledge, the insatiable curiosity that drives us to peer into the deepest reaches of space and the most fundamental particles of matter, is more profound than ever. We are not just trying to understand our universe. We are trying to understand the nature of all universes and our place within that unimaginably vast tapestry. The universe, our universe, is telling us its story. It began with an incomprehensible burst of energy, inflation, and the slow, steady cooling that allowed matter to form. It will likely end in the cold, dark silence of the Big Freeze. But perhaps, just perhaps, our story is echoing in countless others, across an infinite expanse of realities, each one a unique, yet connected cosmic dream. The journey of discovery is eternal, just like the potential for an infinite number of universes, and honestly, I can't think of anything more exciting than that. The previous chapter left us pondering the mind-bending possibilities of the multiverse, a cosmic tapestry woven with potentially infinite variations of reality, each governed by its own set of rules. We touched on the tantalizing hint of subtle imprints in the cosmic microwave background that might one day offer empirical evidence. But what if those rules, those fundamental constants that define our universe, aren't just arbitrary settings in a vast cosmic lottery? What if there's an even deeper, more elegant truth beneath it all? This brings us to one of the most ambitious and profound quests in human history: the search for a theory of everything. Imagine, if you will, the universe as an intricately designed clock. We've spent centuries, millennia even, diligently observing its gears, understanding how they mesh, predicting its movements. We've discovered the grand, sweeping mechanics of gravity, dictating the dance of planets and galaxies, a cosmic ballet choreographed by Einstein's general relativity. And then we've peered into the minuscule, the subatomic, uncovering the bizarre, probabilistic world of quantum mechanics, where particles pop in and out of existence, and reality itself seems to blur until observed. Here's the rub, though, and it's a big one. These two magnificent theories, general relativity and quantum mechanics, describe their respective domains with astonishing accuracy, yet they fundamentally refuse to play nice with each other. They are the two towering pillars of modern physics, but their foundations are built on different soils. General relativity, elegant and smooth, describes gravity as the curvature of space-time, working beautifully on the grand scales of stars and galaxies. Quantum mechanics, on the other hand, describes the other three fundamental forces, the strong, weak, and electromagnetic forces, as mediated by discrete packets of energy, or quanta, acting at the tiny scales of atoms and particles. When you try to combine them, when you try to apply the quantum rules to gravity, or the smooth space-time of relativity to the quantum realm, the equations break down. They give us infinities, nonsense, a chaotic mess that tells us, unequivocally, you're missing something crucial. This incompatibility isn't just an academic inconvenience. It represents a profound gap in our understanding of reality. It's like having two halves of a beautiful, complex poem written in entirely different languages. Where do these theories clash most violently? Think back to the very beginning, the Big Bang, or the heart of a black hole. Places where matter and energy are so incredibly dense, and space-time is so intensely curved that both gravity and quantum effects become dominant simultaneously. At these extreme points, our current physics simply fails. We need a unified theory, a theory of everything, that can reconcile these two titans and describe the entire universe, from its grandest structures to its tiniest constituents, under a single coherent framework. This is where we venture into some of the most speculative, yet utterly captivating frontiers of modern physics. Let's talk about Candace's string theory. For decades, it has stood as one of the most promising candidates for this elusive theory of everything. The core idea is elegantly simple, yet its implications are staggeringly complex. What if the fundamental particles we observe, electrons, quarks, photons, neutrinos, aren't actually point-like dots, but rather tiny, one-dimensional vibrating strings? Imagine a violin string. Depending on how it vibrates, it produces different musical notes. In string theory, the different vibrational modes of these fundamental strings correspond to different particles. One vibration pattern might be an electron, another a photon, another a quark. The beauty of this concept is that it naturally incorporates gravity. A specific vibrational mode of a closed string, a string that forms a loop, is predicted to be the graviton, the hypothetical quantum particle that mediates the force of gravity. Suddenly, gravity isn't an outcast. It's just another note in the universe's cosmic symphony, played by the same fundamental strings. But here's where it gets really wild. For string theory to be mathematically consistent, for these strings to vibrate in a way that makes sense, they require more than the three spatial dimensions we experience: up, down, left, right, forward, backward, plus one dimension of time. Depending on the specific version of the theory, they need anywhere from 10 to 26 dimensions. Most commonly, we hear about 10 or 11 dimensions. Wait, you might be thinking, where are these extra dimensions? I don't see them. And you're right, we don't. The prevailing idea is that these extra dimensions are compactified, or curled up, into incredibly tiny unobservable spaces. Think of it like a garden hose. From far away it looks like a one-dimensional line, but if you get close enough, you see that it has a second curled up dimension. You can walk around it. Similarly, these extra dimensions are thought to be so incredibly small, perhaps Planck scale, 10 to the negative 35 meters, that we simply can't perceive them with our current technology. They are woven into the very fabric of space-time, but on a scale far beyond our direct experience. The specific way these extra dimensions are curled up, their geometry, is incredibly important because it dictates the fundamental constants and laws of physics we observe in our familiar four dimensions. This leads to the concept of the quote 40, a vast number of possible universes, each corresponding to a different compactification of the extra dimensions, and thus a different set of physical laws. This directly ties back to our discussion of the Level 2 multiverse, where eternal inflation bubbles off universes with varying constants. String theory provides a potential mechanism for how those different constants could arise. However, string theory isn't the only game in town. Another compelling candidate for quantum gravity is loop quantum gravity, LQG. While string theory tries to unify all forces by replacing point particles with strings in higher dimensions, LQG takes a different approach. It aims to quantize spacetime itself without necessarily invoking extra dimensions. In LQG, spacetime isn't the smooth, continuous backdrop that Einstein envisioned. Instead, it's thought to be fundamentally discrete, made up of tiny, indivisible atoms of space. Imagine zooming in on the fabric of reality until you see it's not a seamless sheet, but rather a network of interwoven loops, like a quantum chainmail. These loops represent the quantum excitations of gravity, and they define the very geometry of space and time. So space isn't just empty, it's a dynamic, granular structure. A key implication of LQG is that there's a minimum possible area and volume in the universe. You can't divide space indefinitely. This offers a potential way to resolve the singularities at the Big Bang and inside black holes. Instead of an infinite density, there would be a finite, incredibly small, but non-zero volume. Some versions of LQG even propose a quote 42 instead of a Big Bang, where our universe emerged from the collapse of a previous universe, essentially bouncing back from a singularity. Both string theory and loop quantum gravity are profound, beautiful, and incredibly challenging. They offer different visions of the universe's deepest structure, and both face significant hurdles, primarily experimental verification. How do you test a theory that postulates dimensions smaller than atoms or fundamental strings at the Planck scale? It's like trying to weigh a thought. Physicists are looking for indirect evidence, perhaps tiny deviations from general relativity, or subtle imprints in the cosmic microwave background, or even exotic particles predicted by these theories that could be detected at colliders like the Large Hadron Collider. The journey is long, but the potential rewards are immeasurable. As we delve into these fundamental theories, we inevitably confront the nature of time itself. Is time a fundamental aspect of reality, a flowing river that carries us from past to future? Or is it an emergent phenomenon, an illusion arising from more fundamental, timeless processes? From a thermodynamic perspective, time has an arrow, the arrow of entropy. The universe tends towards increasing disorder, from an ordered past to a disordered future. Your coffee gets cold, your house gets messy. The universe expands and cools. This is the wee thermodynamic arrow of time. Then there's this cosmological arrow of time, tied to the expansion of the universe. As the universe expands, it ages. And finally, the psychological arrow of time, our subjective experience, our memories of the past, our anticipation of the future. These arrows generally point in the same direction. But in the equations of fundamental physics, at the quantum level, time often seems reversible. There's no inherent arrow. This has led some physicists to propose the block universus concept, where all moments, past, present, and future, exist simultaneously, like frames in a film reel. Our perception of, quote, 43, moving through time would then be an illusion, a trick of consciousness. If a theory of everything truly unifies physics, it must also provide a consistent understanding of time's role. Does it dissolve into a timeless landscape at the deepest level? Or is its flow a fundamental property that emerges from the vibrating strings or quantum loops? This quest for a theory of everything also brings us full circle to the fine-tuning problem. Remember how we marveled at the incredibly precise values of fundamental constants that allow for stars, galaxies, and life itself? If a complete toe exists, will it explain why these constants have exactly the values they do? Does the theory itself uniquely determine these values, showing them to be the only mathematically consistent possibility? Or does it, as string theory's quote 44 suggests, allow for a vast multitude of possibilities, leaving the anthropic principle that we observe the universe we do because it's the only one capable of supporting observers as the primary explanation for our existence? The implications of finding a theory of everything are staggering. It wouldn't just be another scientific discovery. It would be the ultimate revelation about the nature of existence itself. It could tell us not only how the universe works, but perhaps even why it works that way. It could provide a unified language for all phenomena, from the birth of the cosmos to the inner workings of a human mind, though the latter is a far more complex challenge. This is not to say we're on the verge of cracking it. The challenges are immense, both theoretical and experimental. We're probing the very limits of our understanding, using tools that range from super colliders smashing particles at incredible energies to telescopes peering back to the dawn of time, searching for echoes of these fundamental truths. The journey is fraught with false starts, unexpected turns, and moments of profound insight. But here's the truly exhilarating part. We are living in an era where these questions are not just philosophical musings, but active areas of scientific inquiry. We are collectively pushing the boundaries of what is knowable, driven by an insatiable curiosity about the universe and our place within it. We are the universe, in a sense, trying to understand itself. And the more we uncover, the more we realize the breathtaking complexity, elegance, and sheer wonder of this cosmic story. The pursuit of a theory of everything is not just about equations. It's about understanding the very fabric of reality, the ultimate answer to quote 45 quote, and perhaps even a glimpse into quote 46 quote. What a time to be alive, to witness this unfolding drama of discovery. The universe, in all its perplexing glory, continues to invite us deeper into its mysteries. The search for that ultimate understanding, for a theory of everything, isn't just an intellectual exercise. It's a quest to decipher the very language of existence. Imagine for a moment having that theory in your hands. It wouldn't just be a set of equations, it would be a blueprint for reality itself, a cosmic instruction manual that explains not only how the universe began and where it's going, but why it behaves the way it does, from the smallest quantum foam to the largest galactic supercluster. It would tell us if space and time are truly fundamental, or if they emerge from something even deeper, like the vibrations of tiny strings or the granular structure of quantum loops. If our universe is indeed a symphony of vibrating strings, as string theory suggests, then everything you see, feel, and are, every atom in your body, every star in the sky, every thought in your mind, is just a different vibrational mode. Think of a guitar string. Pluck it one way, you get one note. Pluck it another, you get a different note. In string theory, these notes are the fundamental particles of reality. Electrons, quarks, photons, gravitons. It's a breathtakingly elegant idea, suggesting that the seemingly disparate particles and forces are all manifestations of one underlying entity. And if loop quantum gravity is closer to the truth, then space-time itself isn't a smooth, continuous fabric, but a shimmering, interwoven network of discrete, indivisible quanta, like tiny pixels forming a cosmic image. Your very existence, your movement through space and time, would be a dance across these fundamental loops. This profound understanding, however, isn't simply handed to us. It's painstakingly earned through relentless curiosity, brilliant theoretical insights, and crucially, an astonishing array of experimental and observational tools. We don't just sit back and ponder. We actively probe, listen, and gaze into the cosmos, pushing the boundaries of what's detectable. How do we even begin to test such mind-bending theories? How do we peer into the quantum realm or listen to the echoes of the Big Bang? We do it by building the most incredible machines ever conceived, instruments that allow us to either recreate the universe's earliest, most extreme conditions, or to capture its most ancient and subtle signals. Take, for instance, the Large Hadron Collider, LHC, nestled deep beneath the border of France and Switzerland. This isn't just a big machine, it's a time machine, a colossal scientific marvel designed to smash particles together at nearly the speed of light. Why? Because by doing so, we're essentially rewinding the clock, momentarily recreating the unimaginably hot, dense conditions that existed just fractions of a second after the Big Bang. It's our ultimate microscope, allowing us to scrutinize the fundamental building blocks of matter and the forces that govern them. At the LHC, we've already made groundbreaking discoveries, most notably the Higgs boson in 2012. You see, particles gain mass by interacting with the invisible Higgs field, which permeates all of space. Imagine walking through a swimming pool. The water resists your movement, giving you mass. The Higgs field is like that cosmic swimming pool, and the Higgs boson is a ripple in that pool. Finding it confirmed a crucial piece of the standard model of particle physics, our current best description of how the universe's fundamental particles and forces, excluding gravity, interact. It was a monumental achievement, a testament to human ingenuity and collaboration. But the LHC isn't done. It's still operating, pushing the energy frontier even further. We're searching for evidence of supersymmetry, a theoretical extension of the standard model that proposes every known particle has a heavier. Quote 49. If supersymmetry exists, it could provide candidates for dark matter particles and help unify the fundamental forces. We're also looking for signs of extra dimensions, tiny curled-up spatial dimensions beyond the three we perceive, which some theories, like string theory, predict. Imagine a garden hose. From far away, it looks one-dimensional, but up close, an ant can walk around it, revealing its hidden dimension. The LHC is trying to find the ants that hint at these hidden dimensions. It's a relentless hunt for new physics, for clues that will guide us toward that elusive theory of everything. While the LHC probes the infinitesimally small, other instruments are listening to the universe on the grandest scales, giving us entirely new senses. For centuries, our understanding of the cosmos came primarily from light, radio waves, visible light, X-rays, gamma rays. But now we have a new window, gravitational waves. Think about it. When massive objects accelerate like two black holes spiraling into each other, they create ripples in the very fabric of space-time, like throwing a pebble into a pond. These ripples are gravitational waves, and they travel through the universe at the speed of light, carrying information about the most cataclysmic events. For decades, they were just a prediction of Einstein's general relativity. But in 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, along with its European counterpart Virgo, made history by directly detecting these waves for the first time. It was the sound of two black holes, each dozens of times more massive than our Sun, colliding billions of light years away, merging into an even larger black hole. This wasn't just a confirmation of Einstein, it was the birth of gravitational wave astronomy. We now have a completely new way to quote 51 the universe, one that doesn't rely on light. Gravitational waves can pass through anything, giving us a clear signal from events that would be obscured by dust and gas if we relied on traditional telescopes. We've since detected dozens of black hole mergers, neutron-star collisions, which produce heavy elements like gold and platinum, and we're just getting started. Imagine what else we might hear. The whispers of exotic stars, the echoes from the very first moments of the Big Bang itself, perhaps even clues about the nature of dark matter or dark energy. It's like suddenly gaining the ability to hear after a lifetime of only seeing. And then, of course, there are our eyes on the universe, our incredible telescopes. From the iconic Hubble Space Telescope to the revolutionary James Webb Space Telescope, JWST, these instruments are constantly pushing the boundaries of cosmic vision. The James Webb Space Telescope in particular is an infrared marvel designed to peer back in time further than ever before to witness the birth of the very first stars and galaxies just a few 100 million years after the Big Bang. It's sending us stunning, high-resolution quote 52 of the universe, revealing how structure began to form out of the cosmic dark ages. With JWST, we're not just seeing distant galaxies, we're analysing the atmospheres of exoplanets, searching for biosignatures, chemical traces that might indicate the presence of life beyond Earth. We're refining our understanding of how galaxies evolve, how black holes grow, and how the mysterious force of dark energy continues to accelerate the expansion of the cosmos. These telescopes are our time machines, our cosmic lenses, allowing us to trace the universe's epic story from its infancy to its grand, sprawling present. What's truly remarkable is the synergy between all these approaches. Theoretical physicists propose new ideas, particle accelerators test the fundamental rules, gravitational wave detectors listen for cosmic cataclysms, and telescopes observe the universe's grand narrative. Each piece of the puzzle informs and inspires the others. It's a global, collaborative effort, driven by an insatiable hunger to know. Yet, even with all these incredible tools and the profound knowledge we've accumulated, the universe still holds many secrets close. A theory of everything would be a monumental achievement, but would it answer every question? Would it tell us why the fundamental constants of nature are precisely tuned for the existence of life? Would it explain the origin of consciousness, or why there is something rather than nothing at all? These are the deeper, more philosophical questions that continue to beckon us, remaining at the very edge of scientific inquiry. The journey to understand the universe is far from over. It's an ongoing, exhilarating adventure, a testament to the power of human curiosity and our relentless drive to explore the unknown. We are living in an era of unprecedented discovery, constantly pushing the boundaries of what's possible, unraveling the universe's most profound mysteries, and in doing so, perhaps, understanding a little more about ourselves. What a time to be alive, to be part of this grand cosmic exploration. And if you've found this journey as fascinating as I have, I'd love it if you'd share your thoughts in the comments below, and perhaps even hit that like button to help spread this wonder. We've journeyed through cosmic inflation, dark matter, and the enigmatic dance of dark energy, peering into the universe's deep past with telescopes and listening to its echoes with gravitational wave detectors. We've even dared to glimpse its potential cold, dark future. But as we stand at the precipice of these grand cosmic narratives, a profound question naturally arises, one that brings the infinite expanse right back to the intimate space between your ears. Who is doing all this observing? Who is asking these questions, building these instruments, and piecing together this incredible story? That, my friends, brings us to the ultimate frontier, perhaps the most complex and awe-inspiring phenomenon in the entire known universe: consciousness itself. Think about it. We've explored the universe from the Planck epoch to the potential Big Freeze, from the subatomic to the supercluster. Yet all of that understanding, all of that wonder, is filtered through the lens of a conscious mind. Your mind, my mind, the collective mind of humanity. What is this incredible capacity that allows us to not just exist in the universe, but to ponder its very beginning and end? The universe, in a sense, is telling its story through us. It's an astounding thought, isn't it? That after billions of years of cosmic evolution, from the primordial soup to the first stars, from the birth of galaxies to the formation of planets, the universe has somehow generated systems complex enough to reflect upon its own existence. This isn't just about survival, it's about meaning. It's about the capacity for subjective experience, for feeling, for knowing, for dreaming. Science has made incredible strides in understanding the brain, that 3-pound universe of neurons nestled within our skulls. We can map neural pathways, observe electrical impulses, and even correlate specific brain regions with different thoughts, emotions, and memories. We know, for instance, that your visual cortex lights up when you see this text, or that your amygdala might fire when you feel a sudden surge of excitement. We can even induce certain sensations or memories by stimulating specific parts of the brain. These are monumental achievements, illuminating the intricate machinery of our minds. But here's where it gets truly fascinating, and where science bumps up against what philosophers call the, quote, 53 of consciousness. We can describe what the brain does, how it processes information, which parts are active, but we still struggle to explain why. Any of this activity should give rise to subjective experience. Why does a specific pattern of neurons firing create the feeling of redness when you see a sunset, or the sensation of joy when you hear your favourite song? Why isn't it all just electrochemical reactions devoid of inner life? This is the chasm between the objective, physical processes of the brain and the subjective, qualitative experience of being. We can see the light waves hitting your retina, the signals travelling down your optic nerve, the processing in your visual cortex. But we cannot yet truly explain your private internal experience of seeing red. It's like trying to describe the taste of chocolate to someone who has never had taste buds. The physical description is one thing. The qualia, the subjective quality of experience, is another entirely. Some theories suggest that consciousness is an emergent property, much like wetness emerges from water molecules, even though individual water molecules aren't wet. Perhaps When neural networks reach a certain level of complexity and interconnectedness, consciousness simply arises. It's not a magical spark, but a natural consequence of highly organized information processing. Think of it like a symphony. No single instrument playing alone creates the symphony. It's the complex interplay and harmony of all instruments together that results in the grand, immersive experience. Is our consciousness the brain's ultimate symphony? Other perspectives, like integrated information theory, IIT, propose that consciousness is fundamentally about the amount of integrated information a system possesses. The more integrated and irreducible the information, the more conscious the system. This theory attempts to quantify consciousness, suggesting that even simple systems might have a rudimentary form of it, while the human brain, with its trillions of connections, represents a pinnacle of integrated information. It offers a framework but still doesn't fully bridge that hard problem gap. It tells us what might be correlated with consciousness, but not why it feels like anything at all. This isn't just an abstract philosophical debate. It has profound implications for our understanding of the universe. If consciousness is an emergent property of complexity, does that mean other complex systems in the universe could also be conscious? Could an advanced AI with a neural network far surpassing our own eventually develop its own subjective experience? Could entire planets, or even galaxies, harbour some form of distributed consciousness, a cosmic awareness arising from the vast interconnectedness of matter and energy? These are not questions with easy answers, but they force us to expand our imagination beyond our human-centric view. Consider the possibility of life beyond Earth. We're actively searching for it, using the James Webb Space Telescope to analyze exoplanet atmospheres for biosignatures, for signs of life, perhaps even intelligent life. If we were to encounter another civilization, or even just another species with complex brains, would their consciousness be similar to ours? Would they experience the universe in the same way? Their perception of time, space, and even fundamental reality could be utterly alien, shaped by billions of years of different evolutionary pressures. Imagine a species that perceives in dimensions we can't even fathom, or experiences time non-linearly. Their subjective universe would be a tapestry woven with threads entirely foreign to our own. This brings us back to the anthropic principle, which we touched upon previously. Is the universe fine-tuned for life, and by extension, for consciousness? Or does consciousness simply arise in whatever conditions allow for sufficient complexity? Some argue that the very act of observation, of conscious awareness, plays a role in shaping reality, a concept that dances on the edge of quantum mechanics and philosophy. The idea that the universe, in some fundamental way, requires an observer to fully quote 57 its wave function is a powerful and unsettling thought. It suggests a deeper, more intertwined relationship between mind and cosmos than we often consider. But let's ground ourselves for a moment. Right here, right now, you are conscious. You are experiencing this moment, processing these words, perhaps feeling a sense of curiosity or wonder. This is a miracle in itself, a testament to the incredible journey of matter and energy from the Big Bang to your brain. Your consciousness, as fragile and fleeting as it may seem on a cosmic timescale, is the universe's way of knowing itself. It's the universe's way of reflecting on its own grandeur, its own mysteries, its own potential future. As we look towards the far future of the universe, that eventual big freeze, that cold, dark, empty void, we are confronted with another profound question. What happens to consciousness then? If it is purely a biological phenomenon tied to the intricate dance of neurons, then it will inevitably cease with the death of stars and the cooling of the cosmos. The universe will become a silent, indifferent tomb, its story untold. Or could consciousness, in some form, transcend its biological origins? Could it be uploaded, digitized, perhaps even diffused across the vast computational networks of a future post-biological civilization? Imagine minds existing not in fragile organic bodies, but as intricate patterns of energy, capable of surviving for eons, exploring the dying embers of the cosmos, perhaps even finding a way to escape the ultimate heat death. This is the realm of speculative science, of course, but it highlights our innate human desire to overcome the limitations of our physical existence, to preserve that spark of awareness that makes us us. The search for a unified theory of everything, for a grand explanation of the universe's fundamental laws, often focuses on particles, forces, and space-time. But a truly comprehensive theory, some argue, must also account for consciousness. How does subjectivity fit into the objective framework of physics? Is it an epiphenomenon, a byproduct that has no causal power? Or is it a fundamental aspect of reality, a feature of the universe that is as intrinsic as gravity or electromagnetism? These are the kinds of questions that keep us up at night, that drive scientific inquiry, and that inspire philosophical contemplation. They remind us that for all the incredible progress we have made in understanding the external universe, the internal universe of our own minds remains a vast, largely unexplored territory. The journey to understand consciousness is, in many ways, the ultimate journey of self-discovery, both for us as individuals and for humanity as a whole. So, as we continue to push the boundaries of our knowledge, as we build even more powerful telescopes and particle accelerators, let's not forget the most incredible instrument of all, the conscious mind. It is the lens through which we perceive reality, the engine of our curiosity and the vessel for our wonder. The universe is a grand narrative, but it is our consciousness that gives it meaning, that asks the why questions, and that dares to dream of understanding it all. What an extraordinary privilege it is to be a part of this cosmic story, to be the universe's way of looking back at itself. And what an incredible mystery still lies within us, waiting to be unravelled. We've journeyed through the universe's explosive birth, its cosmic adolescence, and peered into its frosty, distant future. We've wrestled with the invisible giants of dark matter and dark energy, and even dared to glimpse the elusive, bubbling foam of the multiverse. But as we stand at the precipice of all this knowledge, a final, perhaps the most profound, question emerges, echoing not from the distant reaches of space, but from the very core of our own existence. Why are we here to ask these questions at all? Remember how we talked about consciousness, that baffling phenomenon that allows you to experience the vibrant tapestry of reality, to wonder about the cosmos. It's a remarkable thing, isn't it? This universe, the unimaginably vast and complex system, has somehow, through billions of years of cosmic evolution, given rise to beings capable of contemplating its own origins and destiny. We are the universe's way of looking back at itself, of telling its own story. It's almost as if the cosmos developed a mind, and that mind is us. But then you start to notice something peculiar, something that has puzzled scientists and philosophers for decades, even centuries. It's a concept we call, or I quote 15. Imagine, if you will, a cosmic control panel bristling with dials and sliders, each one representing a fundamental constant of the universe. We're talking about the strength of gravity, the mass of an electron, the precise value of the cosmological constant, the ratio of the electromagnetic force to the strong nuclear force. All these seemingly arbitrary numbers that dictate how the universe behaves, how atoms form, how stars ignite, and how galaxies coalesce. Now picture yourself adjusting just one of those dials ever so slightly. What happens? Well, if the strong nuclear force which binds protons and neutrons together in atomic nuclei were just a tiny bit weaker, hydrogen would be the only element in the universe. No carbon, no oxygen, no iron. No building blocks for stars, planets, or critically life as we know it. If it were slightly stronger, hydrogen wouldn't exist, and the universe would be a very different, very sterile place. Or consider the cosmological constant, that mysterious energy inherent to the vacuum of space, driving the accelerating expansion of our universe. We've talked about how it's leading us towards a big freeze, but if its value were just a little bit larger, the universe would have expanded so rapidly in its infancy that matter would have dispersed too quickly to ever form stars or galaxies. If it were a little bit smaller, gravity would have quickly reasserted itself, leading to a rapid collapse back into a big crunch before life could even begin. The odds of it being just right for a universe like ours, capable of supporting life, are astronomically small, something like 1 part in 10 to the 120. That's a 1 followed by 120 zeros. It's a number so vast it defies comprehension. It's like hitting a bullseye on a target the size of the entire observable universe with a single, random shot. This isn't just about things being convenient for us. It's about the fundamental laws and constants of physics being exquisitely balanced to allow for the very existence of complexity. It tells us that if these dials were nudged even fractionally in almost any direction, we wouldn't be here. There would be no stars, no planets, no carbon, no water, no conscious beings to ponder the cosmos. The universe would be a barren, featureless wasteland, or perhaps wouldn't even exist in a recognizable form. So, what do we make of this astonishing cosmic coincidence? Is it truly just a roll of the dice, an incredibly lucky draw from an infinite number of possibilities? This is where the anthropic principle enters the conversation, a concept as fascinating as it is controversial. At its core, the anthropic principle simply states that the universe must be compatible with the conscious and intelligent life that observes it. There are different flavors of it. The Siam, weak anthropic principle, suggests that we simply observe the universe to be the way it is because, if it were otherwise, we wouldn't be here to observe it. It's a bit of a tautology, a self-evident truth, but it doesn't really explain why the universe is so finely tuned. It just says, well, of course it is, otherwise you wouldn't be asking. Then there's the more provocative, strong anthropic principle, which posits that the universe must have properties that allow for life to develop at some point in its history. Some interpretations even go further, suggesting that the universe is somehow designed for the emergence of observers. This takes us into philosophical and even theological territory, which, while deeply human, often lies beyond the realm of testable science. But for many scientists, the fine-tuning problem, coupled with the anthropic principle, points to a different, more scientifically grounded, yet still mind-bending solution: the multiverse. Remember our discussion of Level 2 multiverses born from eternal inflation. The idea is that our universe isn't the only universe. Instead, there's an endlessly inflating 61 that constantly bubbles off new universes, each with its own unique set of physical laws and fundamental constants. If this is true, then the problem of fine-tuning suddenly looks very different. It's no longer a cosmic lottery win for our universe alone. Instead, it's like going to a cosmic casino with an infinite number of slot machines, each one programmed with slightly different rules. If you play enough of them, you're bound to hit the jackpot on one. In this scenario, our universe is simply one of the countless bubbles where the dials just happen to be set exactly right for stars to form, for carbon to exist, for planets to coalesce, and for life to emerge. We're not special because our universe is uniquely perfect. We're special because we happen to reside in one of the universes that could support us. The vast majority of other universes would be sterile, lifeless, and unobserved. The multiverse concept offers an elegant, if unproven, solution to the fine-tuning problem. It shifts the question from quote 62 to quote 63. It's a compelling argument, isn't it? It grounds the seemingly miraculous existence of life in the sheer statistical probability of an infinite cosmos. However, the multiverse, for all its explanatory power, brings its own set of profound challenges. How do we test it? How do we prove that these other universes exist? By definition, they are beyond our observable horizon, perhaps even beyond the reach of any conceivable experiment. We can look for subtle imprints on the cosmic microwave background, echoes of collisions with other universes, or gravitational effects from higher dimensions. But these remain highly speculative and incredibly difficult to detect. This is where the boundaries of science become hazy, blending with philosophical speculation. Are we simply creating a bigger, untestable framework to explain away a cosmic puzzle? Or is it the logical next step in our understanding of reality? This quest for understanding, this relentless push into the unknown, often leads us to question the very nature of reality itself. We've explored matter, energy, space, and time. But what if there's another fundamental ingredient? What if information is as fundamental as mass or energy? Think about it. From the quantum entanglement of particles to the intricate genetic code within your DNA, information seems to be woven into the fabric of the cosmos. When a black hole evaporates, it's not just energy that's lost, it's also information. Scientists like Stephen Hawking and Leonard Susskind have grappled with the quote 64 of black holes, suggesting that information is never truly destroyed, but rather encoded on the event horizon. This implies a universe where information is conserved, perhaps even fundamental. If information is truly fundamental, what does that mean for our universe? Could our reality itself be a vast, complex information processing system? This idea, while firmly in the realm of theoretical physics and philosophy, has gained traction in certain circles. It leads to the provocative concept of the simulated universe. Are we in fact living inside an incredibly sophisticated simulation, perhaps run by a far more advanced civilization? It sounds like science fiction, I know. But consider the progress of our own computing power. If civilizations continue to advance for millions or billions of years, their ability to create incredibly detailed conscious simulations could become indistinguishable from reality. And if such simulations are possible, and if there are many of them, then statistically it might be more likely that we are in a simulation than in the quote to 65% reality. It's a dizzying thought, isn't it? Every star, every galaxy, every thought you've ever had, all just lines of code in a cosmic program. This idea, whether you find it unsettling or exhilarating, forces us to confront the limits of our perception and our understanding. If we are in a simulation, could we ever detect it? Could there be glitches in the matrix, subtle inconsistencies in the laws of physics that hint at the underlying code? Or is the simulation so perfect that it's simply our reality, full stop? Ultimately, this journey through the beginning and end of the universe, through its deepest mysteries and its grandest possibilities, brings us back to ourselves. It is our curiosity, our intellect, our insatiable drive to understand that propels us forward. We are the universe's self-aware explorers, charting its vastness, deciphering its ancient messages, and grappling with the profound implications of its existence. The universe doesn't offer easy answers. It presents us with an unending series of questions, each one leading to another, deeper layer of mystery. But that, my friends, is the true magic of science. It's not just about finding answers, it's about learning how to ask better questions. It's about pushing the boundaries of what we know and embracing the humbling yet awe-inspiring realization of how much we still have yet to discover. The cosmos continues to challenge us, to expand our minds and to remind us of our tiny yet profoundly significant place within its grand unfolding story. And as long as we keep looking up, keep questioning and keep exploring, the universe will continue to reveal its secrets, one wondrous discovery at a time.